So we want to see how we can make this chart, and we want to see some questions about this. Remember, for every chart, as I said, for every chart you need average. You need average. So this here, you will be looking for average proportion. And then you also need the upper control limit. And then you need the lower control limit. Whether you're doing mean, whether you're doing proportion, whether you're doing range, you need these three on your chart. Okay, you need these three on your chart. So with proportion, you are not dealing with mean, first of all. You're not dealing with a range. So you'll be having data. For example, let's look at question 7. On the required part, we are told to determine the mean proportion of defective data entries. The mean proportion, this word is very, very key. You are told to determine the mean proportion. Mean proportion is like the average proportion. The same way they can say you look for the mean range. Mean range is the average range. Okay? So we want to know how can we get the mean proportion of defective data entries. Here there is also this keyword, defective. Next time they can put the mean proportion of correct data entries. So you need to be very, very sober or attentive when you're reading these statements. So Roman 2, they are telling us we determine the upper and lower control proportion of defective data entries. Then we construct a control chart for the proportion of defective entries among the data and comment on the process of entering data at Abacus Credit Microfinance. So we are told that the accounts clerks at Abacus Credit Microfinance are responsible for posting each transaction on the customer's credit card. To guard against errors and complaints, inspectors recheck the entries before the close of a day's work and record any discrepancies. Okay, the checked work revealed the data in the table below. Okay, we have clerks. These are different staffs, and each clerk is supposed to inspect the number of transactions inspected, you have the number of transactions inspected. The inspector inspected 200 transactions entered by each clerk, and out of the 200 entered by each clerk, the inspector found out that out of the transactions entered by clerk A, 4 had the discrepancies or errors. Okay, and also here you see that these ones also are from the data revealed. You are in a position to see the number of discrepancies for each clerk. Okay, those are like errors. Okay, so how do you get the proportion? Here you need the proportion of defective data entries. So out of, let's say, you have inspected 200 transactions. So what is the proportion of defective data entry? It's 4 out of 200. Proportion is like the percentage of error. It's like the percentage of error. Okay, so how are you going to get this? You're just going to make a table in your book. Let's start. You make this table, you rearrange your data, like the same way we arrange the data when we are looking for range and mean. Let's rearrange the data. We are from row to column, from row to column. Okay, so you give a number of transactions inspected and number of discrepancies. So here let's add the column 4. Let's add the column for proportion. Add the column for proportion. Please let's do this together. You add the column for proportion. And how do we get proportion? You simply get the number of discrepancies. You get the number of discrepancies, then you divide by the total number of transactions inspected. Okay? You can round off to decimal points to avoid the issues. Okay? You do the same for all, you get 6 divided by this. So it's not a must that you will always have the same number of transactions inspected. For A, you can have 200 and find that B, you have inspected like 300 or 100. So don't cram that it will always be the same number of transactions inspected. No, they can be different. Okay, so you do the same for all. Get the number of discrepancies divided by the number of transactions inspected. Okay, so what is our total proportion? You add everything. What is our total proportion? We add everything here. Okay, and how do you get mean? How do you get mean? We are going to get the total proportion. We divide by the number of sample. How do we get mean? You get the total proportion divided by number of samples. How many samples you have sampled? How many cracks? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we are going to get our total proportion. We divide by the number of samples, 8. And that is our mean proportion. The total proportion, which is 0.25, then divided by the number of samples. Number of samples, there are 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's how you get mean proportion. That's how you get mean proportion. Okay. But I don't encourage you to always use this. You can just use the first approach is better. Or if you want to get the mean proportion, you get the total number of defectives. And what is the total number of defectives? You add here. You add the total number of defectives, you add. Then you divide by the total number of items sampled. Now the total number of items sampled, these are not number of samples, these are total number of transactions sampled. So you get the total number of transactions sampled. Okay, so you get your number of defectives, that is 50. 50, then you divide by the number of transactions inspected or sampled. So if you get 50 divided by 1,600, you will get the same answer. You will get the same answer. Okay. So that's how you get the mean proportion of the defective data entries. Assume they said you look for the mean proportion of the correct proportion of the correct data entry, sorry. Then you create the column for the, of course you will create the column. You have the discrepancies, then you create the column for the number of correct entries. Because these ones are errors, right? This is where you have errors. So can you use the data given to get the number of correct data entries? So if you sampled 200 and you found that out of 200, 4 have errors, so how many transactions are correct? You get the 200, then you subtract the error, the number of errors or the number of discrepancies. You do the same, get the total transactions minus the total errors. You do the same. You do the same for all. You do the same for all. Then how will you get the proportion of the correct data entry? How will you get the proportion of the correct data entries? You get the correct number of correct data entries, then you divide by the total number of transactions inspected. You do the same. You get the number of correct entries, you divide by the number of transactions inspected. That's how you will be getting the proportion of the correct data entries. In a scenario where the examiner has said that you look for the mean proportion of the correct data entries. Here you're looking for the mean proportion of the defective. But in the next question, you can find that here he has said that you look for the proportion of the correct data entries. Is that clear? Is that clear? After getting your proportion here, you follow the same. You get the total, you get the sum, you get the sum, and substitute in the formula. You substitute in the formula the same steps. You get this divided by number of samples. So this one would be what? Would be this divided by 8. And that's what you get. Okay? If I told you are dealing with the correct data entries. Okay? Even if you do the same here, you add, you will get the same answer. If you want to use the second formula of getting the total number of correct entries, then you divide it with, if you divide it with what? With the total number of transactions inspected. If you do, you get this divided by 1,600. I believe you will get the same answer. Okay. So next time, if they ask you to look for the mean proportion of correct data entries, don't be confused. You have to rely on the number of discrepancies to get the number of correct data entries by simply getting the number of transactions inspected minus the total errors. 200 minus 4, you get this. 200 minus 6, you get this. Okay? So Roman 2, we are told. Any question on Roman 1? Roman 2, we are told that we determine the upper and lower control proportion of defective entries. Upper and lower. How do we get that? How do we get that? We have the formula that we follow. This is the formula that we follow. Please, you write it very well. You write it very well. As you determine the lower control and upper control, this is the formula that you will always use, this one. Are you in a position to see the formula? Someone to confirm?
Abel, sorry. How about choosing the first formula?
Your network is
1,000. Sorry, can you first go back to the working, to the table? Can you please first go back to the table? I just want to confirm something. Why did you divide again by 1,600?
Here we have two formulas. As we determine mean proportion, we have two formulas.
Okay.
We have two formulas. You can use this one, you can use this one. So it all depends, but this one is better. Now you recommend you use the first one. So
Okay.
if you use the second formula, you get the total number of defectives, which are 50. Number of defectives are here, you add. Then over number of items sampled. Number of items, these are number of transactions inspected. What is the total number of transactions inspected? You add all this. That's where you are getting 1,600, and I substitute in the formula. You get the same answer.
Which number of samples did you use on the first formula for the correct?
Here number of samples. Here number of samples. You count to get this total proportion. How many items you actually add?
Okay, I've got it. Thank you.
They are 8. Are we together?
Yes. Yes.
Yeah. So you
Thank
get 0.25 divided by 8. You get this. Any other question?
No. Clear now. Thank you.
All right.
I'll go with the first formula.
The first formula is easy. Okay. So next Roman 2. And remember, this question 7 is December, is actually December 2020. Question 4C. Okay. So Roman 2, how do we get lower control limit or upper control limit for proportion? Please, this is the formula. This is the formula we use. Here P bar is average proportion. This one, the one you have above. Then you have N bar. N bar is like your average. Is like your average what? Your average sample. Okay. Or your average. You can call it the number of N. Your N, you can call it the average items sampled. That is total transactions sampled divided by number of transactions. To get this N, please don't confuse this N. Don't take this N as sample. You will make a mistake. This N bar is the total transactions sampled, then divided by the number of transactions or the number of samples. Okay, and this 3 is not cube root. This is 3 times whatever you get under square root. It is 3 times whatever you get under square root. Okay, so we are going to first get the lower control limit. So how do we get the lower control limit? Going back at our formula. Going back at our formula. Okay, going back at our formula. P already we have the average proportion. This is the average proportion. You have it already. Okay, are we together, colleagues? You have the average proportion or the mean proportion. So where you have P bar, you put the figure you have on Roman 1. Then minus 3. Then take square root of what? The formula is saying you put the average proportion. That's what I'm putting. Then times 1 minus the average proportion. 1 minus the average proportion, you close bracket. Then over what? Over any bar. And how do you get any bar? You get the total. The total transactions sampled. The total transactions sampled are how many? Number of transactions inspected. You add all these ones and get the total number of transactions inspected or sampled. Then you divide by the number of transactions, or you divide by the number of samples, which is 8. So the total you will get 200. So where you have any bar, put what? Put 200. Okay, I want you use your calculator now. Please get your calculators and we do it together. Get your calculator and we do this together. So on your calculator, you first deal with this one. You first deal with this one. So open bracket, then write this one times open bracket 1 minus this, close bracket and close bracket. You start with opening bracket, the first bracket, then you say this 0.03125 times open bracket 1 minus 0.03125, then you close bracket. If you close bracket, the first bracket you are closing this one, then close bracket again. Then over, on your calculator, you say divide by 200. Then click on your equal sign. The answer you get, before you remove that answer, you can click on the square root. Click on the square root, then click on the answer. Where on your calculator you have the button having answer. You click on the answer, then equal signs. Okay. Colleagues, are you following what I'm saying?
Yes, we are following.
So once you click, after doing this, click on equal signs, you will have the answer on the calculator. When that answer is still there, click on the square root sign on your calculator, then press on the button having answer. Then press on equal signs. Okay? After getting that, you multiply by 3. Tell me, what do you get? 9. That's what you have? After multiplying by 3, that's what I have. Then when this answer is still
yes,
on the
I've gotten that one.
You have this one.
Which one?
Yes.
Tell us how you got the answer.
So when this answer is still on your calculator, Now let's write this. So we write 0.03125 minus answer. Then you will have negative 5.6594, then times 10 power negative 3. That's what you have. Colleagues, if you're not getting these things, tell me, we repeat. Understand how to use the calculator. Try to understand how to use the calculator. Do you have this as your final answer on the calculator?
Yes, I've got that.
So what does this one mean? It means that if you have this, I tried to write like in this form. It is negative 5.6 times 10 power negative 3. So if I want to write that in decimal points, I start with 0 point. I start with negative 0 point, then I write zeros, it is like 0 point, then I count. This 5 should come in the third place. So I write 0, 0, then 5 must come in the third place. If you have power negative 4, then 5 should come in the fourth place. If you have power negative 2, then 5 should come in the second place. If it is power negative 2, 5 coming in the second place. Okay. If it's power negative 4, you write 0, 0, then 5 come in the fourth place. Have you understood that? So that's why I have this. So you can say negative 0.000056. May I just stop on 5? Okay. So for you, you can say negative 0.000, no, negative 0.0056, which is also okay. Okay, so you can write this. So finally, if you round off to 2 decimal points, you will get negative 0.01 if you round off to 2 decimal points. If you round off to 2 decimal points. Colleagues, are we together? Are we together
Yes.
on this?
Yes.
So you
Yes.
use the calculator. You use your calculator now again to get the upper control limit. You use your calculator to see whether you can get this answer. You use your calculator. Now, because you're looking for upper control limit where there is a negative, you put a plus. Remember the formula was minus or plus. If you're looking for the lower, you use a minus. If you're looking for upper, you use a plus. But other things remain the same. So you use your calculator to see whether you're getting this. Put some speed. Put some
I'm
speed.
getting 0.06815.
Like this one, eh?
Yes.
Okay.
0.7.
And you see, if you're doing this, it should be even better. Get 3, whatever you have, then you write it here. Like that when you're handling Roman, this upper control limit, you will be just substituting, you just put a plus, because already you'll be having 0.0369 up. Where are you getting 0.0369? The square root of this times 3. Okay, so that's how we get upper control limit and lower control limit. Then how do you plot? The same way. Vertical axis, you'll have the sample proportion. Then on horizontal axis, you'll have the samples. Those are your cracks. Okay. You will have on your P chart, you will have a horizontal dotted line showing the upper control limit. You have a horizontal dotted line showing the lower control limit. You have the average, also the dotted line showing the average. The same way we did for the control, the mean and the range. So you are plotting the sample proportions against the cracks. Okay, here we are not plotting against period. We are plotting against cracks or the samples. So these are proportions you're plotting on vertical axis. You're plotting against these ones. On horizontal, you'll be having A, B, C, D up to H. Then on vertical axis, you come up with a suitable scale. Just a minute. We have to plot. We have to plot. So
Still the same page. P chart together together everyone can make it. Horizontal dotted line showing upper control for proportion.
okay. What about now?
The graph.
Okay, so this is the chart, the control chart for proportion. On vertical axis, you put sample proportion. On vertical axis, you put sample proportion. Then on horizontal axis, you put your cracks, A to H. Are we together, colleagues?
Yes.
But you must come up with a suitable scale. You must come up with a suitable scale on vertical axis. Don't just rush, because on vertical axis, you want to plot. On vertical axis, you want to plot even the upper control limit. So as you come up with a suitable scale, you must make sure that your upper control limit or the highest value from your values, from all your proportions, you look for the highest value. The scale you're coming up with must be in a position to help you to get the highest value, which is 0.06, 0.08, sorry. That is the highest value, because the upper control limit is actually 0.07 if you round off to 2 decimal points. Okay, and I encourage you, when you're plotting, don't exceed 2 decimal points. Otherwise, you'll be giving yourself hard time. Okay, so the suitable scale, we can use a scale of 1. It still work. 0.01. It can still work. Remember, as I told you, you get the highest value minus lowest value, then divide by the number of arcs. How many arcs do you have on the vertical axis? If you have 10 arcs, you divide by 10. If you have 8 arcs, you divide by 8, to know the suitable scale. It can give you the hint. It can give you the hint, to know the suitable scale. So yeah, I'm using a suitable scale of 0.01. Then I start plotting. You're plotting what? You stand where you have A on horizontal axis, then you look for 0.02 on vertical axis. You stand where you have A. This is A. This is A. Then look for 0.02. Put like a dot. Then you stand where you have B. Look for 0.03. You do like that. You stand where you have C, you look for 0.03 on vertical axis. Then at the end, you join using a ruler. You join using a ruler. Join your points from A to H using a ruler. Now, after that, remember on your chart, you must have a line indicating upper control limit. You must have a line indicating average. You must have a line indicating lower control limit. So our upper control limit is 0.07. So this is the line showing. This is the line showing the upper control limit. I put like a dotted line indicating that this is my upper. I name this line as upper control limit proportion. Then the average, our average was what? Our average was what? Our mean proportion was what? Our mean proportion was 0.03 here. So I look for 0.03. So I look for 0.03 on the graph. Okay. I look for 0.03 on the graph. 0.03 is here. Is here. So I also put a dotted line or a line. This is your average. This shows your average. Then I also look for the lower control limit. Remember, your lower control limit is negative what? Your lower control limit is negative what? Negative 0.01. So where do you get negative 0.01? Down. Negatives are down. Negatives are down. So negative 0.01 is around here. Around here you put a line. You put a line. Okay, and that will be all for you. That will be all for you. That will be all for your control chart. Comment whether the process is in control. Colleagues, is this process in control? Based on the explanation I gave you last time, is this process in control?
No.
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 This
It's not.
it's not in control. So you will say since there is a point which is above the upper control limit, it means that the process is not in control. The process is not within the control. Okay. So colleagues, that's all. You will use the same knowledge. You will use the same knowledge to answer the last question. Use the same knowledge to answer the last question, question 8. You just rearrange, rearrange your data, then you create the column for proportion. The average fraction. Average fraction is like the average control limit, the 3 sigma control limits. Those are your lower control limit, upper control limit, and the 3 sigma control limits are lower control limit, upper control limit, and average. Okay. Here you are not told to plot. You're just going to determine, calculate the upper control limit, lower control limit, and the average. Already you will be having the average, so you don't need to look for that average again. But for practice, go ahead and plot. Any question about control chart?
And also, that if they ask the 3 sigma control limits, they are just asking for lower and upper limits.
Yes, just that sometimes they may not ask you average fraction of defective, and they say determine the 3 sigma control limits. In the situation where they have not said you determine average fraction in Roman 1, then this 3 sigma control limit will include also the average. Are we together?
Average fraction is the mean proportion, not so?
Yes, the fraction is proportion.
Okay.
So you rearrange this data like the way we rearrange it from the first question. You rearrange your data in this form, having the packs like that, then you get the fraction or the proportion. This one you don't need it. Don't need it. Just I was explaining.
Okay.
So that's all. That's all.